Welcome everybody. In this video we introduce the concept of limits. Limit is the most important concept in calculus, and it is the concept that makes calculus different from algebra. Calculus examines how a change in one variable affects another variable, and we use the concept of limit to study such effects. So consider f of x is equal to x plus 3, and for values of x, so we want to look at this function for values of x close to 2. So notice from this graph that as values of x gets closer and closer to 2, the values of the function f of x gets closer and closer to 5. So this idea that as x gets closer and closer to 2, f of x gets closer and closer to 5, this idea is expressed in this notation here. The way we read this notation is that is this limit of f of x as x approaches 2 is equal to 5. So notice that when I am looking at saying this, I am not really interested in the value of the function when x is equal to 2. I am interested in the value of the function when x is close to 2 but not equal to 2. So notice that, so we are saying that as x gets closer and closer to 2, the value of f of x gets the values of f of x get closer and closer to 5. So one might say, how close? I mean, how do how close can f of x get to 5? Well, you can see here that I can make the value of f of x as close to 5 as I like, simply by choosing x close enough to 2. So in other words, I can make the value of f of x to be within any open interval centered at 5 by choosing any x in some suitable open interval centered at 2. So from this picture, that's clear. So once again, notice that we can make the value of f of x to be within any open interval centered at 5 simply by choosing any x in a suitable open interval centered at 2. And that's exactly the meaning of this notation here. Okay, so the definition of limit, this is the sloppy version. The sloppy version of the definition is that this symbol, this notation, the limit of f of x as x goes to c, or x approaches c, is equal to L, the number L, means that the value of f of x is close to the real number L whenever x is close to c but not equal to c on either side of c. The reason I'm calling this a little bit sloppy version of the definition is because it doesn't address how close we can make f of x to L. It is possible that f might not be defined at the number c. So again, when we are looking at the limit of f as x approaches c, we are not interested in the value of f at c. We are interested in the value of f when x is close to c but not equal to c. Here is, I think, a little bit better version of the limit. So the limit of f of x as x approaches c is equal to the number L. This means that the value of f of x can be made as close to the number L as desired simply by choosing any x close enough but not equal to c on either side of c. So this says that, yeah, we can make the value of f as close to L. How close to L? Well, as much as we desire, simply by choosing any x close enough but not equal to c on either side of c. Now, this is still not the full-blown mathematical definition of limit. So again, the function may not even be defined at f of c. So the limit of f at c may exist, but the function may not be defined at c even. Okay, so let me explain the definition of the limit one more time. So when we are looking at the limit of f of x as x approaches c, or as x goes to c, if we so is the limit of f as x goes to c equal to the number L? Well, if we can make the value of f of x to be within any open interval centered at L, simply by choosing any x in some suitable open interval centered at C. If that is possible, then the limit of f at C is L. Again, the limit of f, to see whether the limit of f at c is L, we ask ourselves, can we make the value of f of x to be within any open interval centered at L, simply by choosing any x in some suitable open interval centered at c. If we can, then the limit of f as x approaches c would be L. Here's an example. I have this function g of x, which is 3 times x minus 2 divided by the absolute value of x minus 2. Clearly, the function is not defined at 2, because when x is 2, the denominator vanishes, or the denominator becomes 0, so it's not defined at 2. So here is the graph of this function. Now notice that the value of the function is always 3 when x is bigger than 2, and the value of the function is always -3 when x is less than 2. How do we know this? By just looking at the function. Well, notice that when x is bigger than 2, then if x is bigger than 2, then x minus 2 would be positive, so then the absolute value signs are unnecessary. So in that case, when x is bigger than 2, the denominator is exactly x minus 2, so I can cancel them out and I get 3. So when x is bigger than 2, you always get the value 3. Now when x is less than 2, then x minus 2 would be a negative number. So then if x minus 2 is negative, then in order to get rid of the absolute value signs, we multiply x minus 2 with a negative 1. So because if we multiply, so again, if x is less than 2, x minus 2 is negative. So if x minus 2 is negative, then negative of x minus 2 would be positive. So negative of x minus 2 would be what I'm going to have in the denominator, and then I can cancel out x minus 2, but then I have a negative in the denominator, so that's going to give me negative 3. So notice that here notice that here the limit of g of x as x goes to 2 does not exist, and the reason is, you see, when x goes to 2, when x is close to 2 on either side of 2, the value of the function does not approach the same number. So when x approaches 2 on the right side, then the value of the function is close to 3. But when x is close to 2 on the left side, the value of the function is close to negative 3. So in this case, the limit of g of x as x goes to 2 does not exist. Now this is a two-sided limit. But for such a function, we can say that the limit of g of x as x approaches 2 from the right side. So by putting a plus sign on top of 2, we are saying that x is approaching 2 from the right side. In that case, the value of the function g of x is getting closer and closer to 3. On the other hand, if by putting a negative sign on top of 2, we are denoting that denoting that x is approaching 2 on the left side of 2. So the limit of g of x as x approaches 2 from the left is equal to negative 3 here. Now these are called one-sided limits. This is called the right-hand limit. This is called the left-hand limit. And so here the right and left-hand limits at 2 exist, but the two-sided limit at 2 does not exist. Now I'm not going to try to be precise with the definitions of the left-hand and the right-hand limits, but the sloppy versions are the following. The limit of f of x as x approaches c from the left is equal to the number k means that f of x can be made as close to the number k as desired simply by choosing x close enough to the number c, but on the left side of c on the number line. And the right-hand limit, the limit as x goes to c from the right side of f of x is equal to the number L, means that the value of the function gets closer and closer to L as x gets closer and closer to c from the right side of c on the number line. Okay, so the limit as x goes to c of f of x is a two-sided limit, and the two-sided limit exists and is equal to L if and only if the right and the left-hand limits of f at c are equal to the number L. So the limit as x goes to 2 from the right of this function is 3. On the other hand, the limit as x goes to 2 from the left of this function is negative 3. So the limit of as x goes to 2 of this function did not exist. So for a two-sided limit to exist, the one-sided limits must exist, and they must be equal to each other. Okay, so given the graph of a function f, we want to discuss the limit behavior of f of x for x near, let's say, 0 here. So here we are given the graph of a function f, and we want to know the limit of f as x approaches 0. Well, if you look at the graph, you can see that as x approaches 0 from either side, the value of the function gets closer and closer to 4 here. So we see that the limit of f of x as x goes to 0 is equal to 4. Okay, the same function, but this time we want to look at the limit at 1. So here you can see that when I can make the value of the function as close to 2 as I desire simply by choosing x close enough to 1 on the right side of 1. So I see that the right hand limit at 1 is 2, but what's the left hand limit at 1? Well, you can see that now I can make the value of the function as close to 3 as I like simply by choosing x close enough to 1 on the left side of 1. So what we have is that the the one-sided limits, they are not equal. So the two-sided limit of f at 1 does not exist. Okay, how about at the number 3? So at the number 3, we see that the function is undefined at 3. However, what's the limit at 3? Well, notice that notice that I can make, let's look at the right hand limit at 3. So I can make the value of the function as close to 2 as I like by choosing any x close enough to 3 on the right side of 3. So the right hand limit at 3 is 2. Similarly, if you look at the left hand limit at 3 is also 2. So the one-sided limits are equal to 2, so the two-sided limit exists, and it is equal to 2. So notice that even though the function is undefined at 3, the limit at 3 does exist and is equal to 2. Okay, so I think I'm going to stop this video here. In the next video, we will start with some properties of the limits.